Welcome everyone for the fourth day and today we will start with the morning session, mostly focusing on hands-on exercises with Johannes Buchner, and then joining by Peter, and everything is yours basically.
Okay, good morning, everyone. I will talk about two topics, and then Peter will talk about something else to sort of, add on to what was talked about yesterday and the day before. So first, I will talk about how to handle backgrounds, how to model backgrounds, and for that, recall our sort of linear story of how we detect X-ray photons. So we have the source spectrum that goes through the response of our instrument. And then we also have this background component that we should add in somehow. But we didn't really talk much yet on how to do that. So that's what I want to do now. So in this linear combination where you have this source spectrum, you apply it to the response, you get sort of this involved in the detector space intensity in each channel. In this sort of picture, you can have two spectra. One, and this is very typical for point sources, where you extract the spectrum where your source is, that would be the blue, and you extract another spectrum in a nearby region, could be an annulus, for example, which just contains the background. And then you have these two spectra, and you can model both of them. And the only difference between the models would be one would contain also the source, and one would only contain the background. Okay, so here, so the red here would be the astronomical source, and green would be the background model. And then you can fit both of these spectra simultaneously and solve both for the background spectrum and for the source, for the astronomical source. Okay, so let's look at some works of how people have done this. This is an example from NuStar, where they try to model all the sources that contribute to the background. And I mean, I'm not an expert on X-ray backgrounds, but there are several components. One component is caused by, for example, protons in the solar wind that directly hits the detector. They don't go through the telescope, they just impact and leave charges on the CCD. And that imprints a relatively flat spectrum that would be the black horizontal line here. So that usually comes up at the higher energies. And then you have also an astronomical background, for example, so for example, active galactic nuclei that populate the entire sky. Many of them you can't actually detect, but the whole population of them produces some emission, and that emission is this cosmic X-ray background. You have another component here that you can sort of approximate by photon index of 1.4. And then so here's so if you have an instrument that goes to softer responses, so down to 1 kV or 0 point something kV, then you also get emission from the local bubble, so the environment of our solar system that has a lot of hot gas. That hot gas is producing plasma emission that produces an additional component. So you can build a model like this, relatively complex, and simultaneously try to fit your source of interest and these background components. They also vary. So, for example, the solar wind varies. and you can also spatially vary. That's a big problem if you want to look at galaxy clusters, for example, where you can't do this, where you don't have a neighboring region which is really free of background. So that's why they really care making a physical model and try to extrapolate to the region. Okay, but sometimes you might not be very interested in this background, and all you care about is that here in the detector channels you have some contamination. So you don't have to do, in this case, you don't have to work in the astronomical flux space. You can just work in the detector space and make a phenomenological model of what's happening in the end. And in this case, you don't care if something went through the telescope response, or it just directly hit your detector. You just model what arrives in the end. Okay. So you can do that, and this is an example for Chandra where I took a background spectrum, so from an annulus, and just came up with a model that consists of broken power law and a bunch of Gaussians to just approximate this shape. And then and try to fit it, and then use that fit to add it to what's contaminating the source in the middle, or scaling by the relative variance. Okay, and the benefits of doing it like this is you can, if you want, you can use some physical knowledge of your detector. For example, you know that this might be a gold line, and you want to model it. It also has the benefit that you're sort of having a model that's continuous over the space. So you don't have each channel, each detector channel doing its own thing. You're imposing some smoothness, so you take advantage of neighboring information. And you don't have a problem if you have 0 counts in one channel, because Poisson statistics takes care of that and the neighboring informing. Drawback of doing this approach is you need to specify some model. It takes a little development time, and sometimes, yeah, you know about minimizers. They can do weird things, so they might go wrong, and you have to sort of have a look at it. In BXA, there are such empirical models implemented for Sherpa, and in particular, there are models for XMM, PN, and MOS, for Chandra ACES, for Swift XRT, that you can use, and it tries to automatically fit that for you. So have a look on the documentation if you're interested in that. A bit more recently, I've been developing this approach to automatically build such models. And this takes advantage of the many years of X-ray archival data that we have accumulated now. So we have, for example, the XMM archive, Chandra archive, NuStar, RxTE, Swift archives. We have a huge amount of data, and we can, and in this case, I obtained these background spectra that actually have been extracted previously. I just determined principal components across these background spectra. There's a technique called principal component analysis, which sort of identifies the various shapes, the most important shapes that turn up in this variety of backgrounds. Okay, and here you see 6 of those principal components, which sort of illustrate the diversity of backgrounds that are seen across NRT channel, the detector. And you see sometimes, for example, the soft end is higher, sometimes it's lower, sometimes the lines are stronger and weaker. And now I have a model with 6 components that I can add, and I can fit this to each background spectrum and be done with it. And so this is implemented for these various detectors, both in PXA, Expect, and Sherpa, and you can also build automatically yourself if you have 1,000 background spectra. You can build a model like this for your particular scenario. Okay, then I want to come to what Expect does by default, this WStat statistic. And that actually happens if you set the statistic to CStat in Expect. It actually uses W statistic. So it does what I'm going to describe now. So you have a spectrum in the background. So you have these detector channels, and you obtain the number of counts. And what it does then, it tries to estimate the count rate in each of those bins by maximizing the Poisson likelihood. And then it scales that estimate and applies it, adds it when you do the analysis. Okay. And this is sort of nice because you don't have to assume model, you don't have to do much, but it has the drawback that there is no well-defined maximum or optimal count rate if you have 0 counts. And actually, 1 count is still a little bit problematic. So if you want to use this, what people usually do is bin up the background spectrum to have 1 or more counts in each bin, and then you can apply this. You don't bin up the source spectrum by its bins, you bin up the background spectrum by how many bins it contains, and then you apply the same binning to the source spectrum. So you shouldn't use group PHA, you should use FT group PHA. So this is, yeah, you don't need to specify a model, that's good. But the drawback here is that this bin doesn't learn about what's going on in the neighborhood. So you don't have this continuity. You also get larger uncertainties than if you use an approach like this or this. And you need to deal with the 0 count. Right, so this is basically what I more or less just said. So what I would recommend is, ideally, you want to model both background and source with Poisson statistics, either with a function approximation or with some physical model. And you want to fit either simultaneously or fit the background model first and then use that to fit this. Okay. First part over. Now let's go to something completely different. Okay, so I told you before that I'm not such a big fan of getting best fits and making histograms of these best fits because they don't contain the uncertainties in the best fits. So what do you do if you want to make a sample distribution, for example, NH distributions of 50 AGM? How do you combine these NH estimates from each source to make a histogram or a sample distribution of what's going on for this particular collection of sources that you have? And I briefly want to introduce hierarchical Bayesian models and give you an definition of how they work. Okay, and I chose to do a little bit of math here, but it's not a slide, so don't panic. Remember we had in Bayesian inference on the left we have the posterior, and that's the prior times the likelihood. And so usually what we have is we have data, which are our photon counts. We have a model, and that model has some parameter, like for example NH, and that parameter is being informed by the data, or in other words, you can predict the data from the model if you assume certain parameters. Okay, so that you have this likelihood, which is a function, you stick in your parameter, and then you need for that parameter also a distribution, which is the prior. Okay, But now let's go one level beyond that and say, well, that prior on that parameter might also have a distribution. We don't know the prior. Okay. So we're gonna use a function or a probability distribution to that of that parameter, but that probability distribution also has parameters. So for example, you have a normal distribution for that parameter with mean, mu, and standard deviation sigma. And so now you're sort of having an additional level here. This parameter is being informed by the sample mean and sample standard deviation. So you have this normal distribution as a prior, but that prior additional. Okay. So you have this prior with 3 parameters, and you still have the likelihood. And now you can separate out this prior into your prior in the sample standard deviation, and you have how that parameter depends on these parameters. Let's just be a normal distribution with normal sample distribution, and here you still have the likelihood that hasn't changed. So essentially, for each object, you have the sample distribution applied to that parameter, and outside that. So for each object, you have the analysis essentially that you had, but on top of that, to all of these objects, you apply a hierarchy. Okay, then we can go one step further. So if you're not actually interested in these individual object parameters, we can marginalize them out. So we integrate over all these functions. We integrate that away. And what you're left with, if you do this with posterior samples, so you did your analysis, you got these posterior samples of theta. And if you did this, if you have your posterior samples, then you can replace that integral with an average, the sum of averages. And since those are already posterior samples, they already follow the likelihood. And so all you have to do is weigh these by whatever is this above population distribution. That only applies if you use a flat prior to analyze these objects. Okay? So that's sort of important. You have to analyze each of your objects with a flat prior. Otherwise, you're going in circles. Okay, so this was perhaps not very intuitive. So let me get a bit more into the practical side of how this works. So let's say you analyzed in one parameter, you analyze each object, you get your posterior samples, and you assume flat prior on this parameter. How do you combine this? Well, you assume a sample distribution on this parameter, and then you compute its probability for each of those posterior samples. You sum within each object, and you multiply across the object. You sum because one of these posterior samples is the true one, and you multiply because it has this assumption has to hold for all objects. All objects have to follow the sample. Okay, so it's a very simple operation, summing and multiplying. And that's actually implemented in posterior stacker, and one of the exercises will be getting some distributions like this out from analyzing, after analyzing these. Okay, so just to give you an example, you have your posterior samples for n objects, and let's say you have 100 posterior samples from each object. You have this 100 times n matrix of posterior samples. Now you apply your particular sample distribution to that. That gives you a probability. And then all you have to do is sum across one axis and multiply across the other axis. Sum across, and then you multiply, and then you have this likelihood, this hierarchical. And then you try out different sample parameters and see which parameters would be preferred. Just to give you an illustration, let's say you have, you measure two objects like this. So you have a posterior for one object like this, for another object like this. And now you choose a population or a sample distribution like the red one, which has some overlap with both. Okay. Oh, sorry. I should say it again. So let's say you observe one object which has this measurement error, and you have the sample distribution, which is the green one. Then sort of the overlap between them would be the red. Okay. So it would be preferable if you move the sample distribution close to where your observations are, and then you get a better integral. So summing would be yielding a higher value. Okay, but if you have two measurements, two objects, then this distribution doesn't cover that object, right? So having a wider distribution that integrates to a good value here and integrates to a good value here will be preferable. It will give you a higher likelihood at the end. So let me just illustrate this a bit further. If you have a bunch of measurements, so I will always get constraints from a measurement 6 plus minus 2 with measurement errors. So initially, I start out with 0 observation. And remember, if you do the multiplication with 0 items, you get 1. So the likelihood is always 1. And that's illustrated here on the bottom, everywhere in the space of the mean and the standard deviation of the distribution has the same probability. And here is what I use for simulating. Now I add the first object. Now, of course, you could put your sample distribution around this with a small dispersion. So you could put it at 9 with a small sigma. That would be okay. But you could also put it far away with a large sigma. And that's this parameter space that's also allowed. Still looking at the likelihood. If you add a second point, you see this putting it at 9 with a small sigma is not allowed anymore. You have to cover both observations. You have this allowed parameter space. And if you keep adding observations, it zooms in to the true value. Then you can play tricks like increasing the error bars. Increasing the error bars. If you make them large enough, suddenly having a sigma of 0 is allowed again, because each of the objects have such a large dispersion that you could get away with having no dispersion. So yeah, this is sort of the behavior of this hierarchical models. They are very useful to apply. So here I show a column density distribution of gamma ray bursts fitted with 3 sample distribution, this Gaussian distribution, this broken power law distribution, and actually a model that has in each bin independent density, or a histogram, fitting a histogram. And here are a few more applications of how we use it. Yeah, so I will hand over to Peter now, and he will also show some more applications of this technique that we.
Should we take questions now or later? Yeah, we wait for office.
Okay, hopefully online can hear me. Thank you. Okay. Oh, no. This one, right? Should I do the desktop or the screen?
It looks like something else is being shared. Like not being.
Okay, so it's not presenting. And then the share screen.
What happens if you just share the back? Can't see you.
When I
In the chat.
yeah.
No, use yours personally.
Yeah.
I'm not connected.
Yeah.
You haven't really talked yet. You haven't really talked yet.
Can you hear me? Hello, can you hear me online?
We can hear you.
Okay. So yeah, thank you very much to Johannes for introducing state hierarchical modeling so nicely. Yes, I was just going to run through a few applications that I've done for my own research to some of these things, and then also talk a bit more relative to the exercises for the second session. Just so that you know, some of the exercises computationally may take rather a long time, so don't worry. Don't worry if it's taking many hours, possibly days. Yeah, that's how they're supposed to. But hopefully there should be enough time to at least do a few of those before the end of the winter school. Okay, so So for the second session of the hands-on exercises, there are broadly speaking 3 main themes. Okay. So the first one is, as Johannes was introducing, this idea of population sample distributions. So if you have a whole bunch of posteriors, how do you then understand the underlying population that you can use with hierarchical modeling? And one caveat, of course, is that it's the sample distribution, but it is quite difficult to be able to say it's the population distribution without having to do other considerations such as biases or things like that. The second point is this idea of we're using, so we've used BXA to calculate things like Bayes factors, Bayesian evidence. We also have things like the C statistic, or if you really want to, chi-squared, right? But it's about trying to figure out what difference in statistic value would actually correspond to favoring one model over another. Okay, and a nice way of doing that is with simulations. And then finally, if you fit a whole bunch of models and the model comparison says that model 10 is better than model 1, does that tell you that model 10 is a good fit? Not necessarily, right? So then you have to start to think about whether a model, whether you can actually verify that model irrespective of the other models that may be ruled out from model comparison. So first up is population distributions. So I don't think I really need to introduce how they're generated, seeing as though Johannes did such a good job. So I was going to basically just do an overview of how I've used this in my research. So a very small bit of background for anyone that don't really study AGN. Here's a sort of a cartoon of some geometry that an AGN could be in. Okay, so you have a supermassive black hole at the center, you have an accretion disk, and then very close to the supermassive black hole, you have this X-ray gas that Compton-Knox gases accretion disk photons in this sort of idealized picture, and then that's where your primary X-ray emission comes from. And somewhere on larger scales out, there's some sort of obscura. Okay, you see this obscuration in lots of X-ray spectra of AGN, and depending on the level of the obscuration measured by the column density, you get a very different X-ray spectrum. Okay, so this is I'm just plotting for a particular clumpy distribution of blobs of gas surrounding an accreting supermassive black hole. If you propagate X-rays outwards, this is the spectrum that you would see, and it's colored by the column density. Okay? But this is for one specific geometry. Okay? So you have to assume an X-ray model, you assume a geometry, and then under that geometry, you get a model fit. Okay? And for my particular research, I'm doing it for a large sample. This is showing a subset of that sample that the majority of them are obscured. And if you flick back to the general sort of shape of the spectrum in this plot, I've plotted the sources so that the spectra should be in the same units roughly on the y-axis. And as you can see, if you look at a particular source, let's say this one, you do see this sort of strong iron line in the center and then rising at higher energies, which is kind of similar to the plot for heavily obscured AGN. Okay, so that's the general idea. Okay, so you can assume one model, one geometry, right? But that's not much fun, right? Because there are many, many different geometries, many more than I'm actually showing here, that you can actually choose to fit your X-ray spectra with. Okay. And it's kind of a natural question to say that can we use model comparison in some way to see if current data is able to favor one geometry over another. Okay. And so that's what I'm trying to do. Now, if you do this, so this is showing every single row in this little plot on the right. Every single row is a different source, but with the column density that you get from fitting with a particular model that was favored because of the model comparison. Okay, so each posterior, so for instance, the first 3 sources on the bottom here are consistent with being very unobscured because they have the lowest MH at around 10 to the 20 here. And then as you get further to this top right corner, you get more and more sources that have the sort of higher column densities under a particular geometry. Okay, Now, the very cool thing here is that if you use something like Posterior Stacker, all of these complex posterior shapes that you see here, so for instance, this particular source, it was pretty unconstrained for the column, right? It's got lots of bumps and wiggles in the posterior. It encompasses that structure of the uncertainties in the posterior into the parent population that you get at. Okay. So, Johannes introduced this very nicely. This is showing, so in addition to the Gaussian model, there's another option for what's called a histogram model. So instead of having the mean and the standard deviation of the model as the free parameters of your parent population, what you actually have instead are, in my particular case, 6 free parameters, which are just the heights of the NH distribution that I'm doing, right? So just the probability of, say, the bin of log NH equals 20 to 21, so on and so forth, up to 26. And that's informed from the individual source spectral fits. So there's individual posteriors that I showed on the previous slide. Okay. So how does this work in practice? So in this GIF here, I'm going through all of those posteriors I just showed you, but I'm just including more and more and more as you go on. And on the left, every single slice of this GIF shows you what posterior stacker is predicting the parent population to be when you consider only those posteriors. Okay. So as you can see, initially, I tried to order it roughly by the column density. As you can see, initially, everything's unobscured. So posterior stacker is saying that, well, unobscured is quite likely. But then as you increase and you include more and more of these sources, even the ones with quite broad uncertainty on higher column densities, you see that the white distribution starts to increase with what's called the Compton thick fraction. So just in this plot, roughly everything above 24 on the x-axis, and until you get a particular Compton thick fraction. I would note that early on, it does say that the Compton thick fraction is relatively high, but within the full uncertainties, it's basically 0, because initially you have no sources with a posterior above 24. Okay. Okay. So that was just a very quick whistle-stop tour of population distributions. So I think it's exercise 2.2 on the tutorial is all about this idea of model selection calibration. Okay. So the main idea here is that you have some null hypothesis. Let's say you're comparing 2 models, right? So in the exercises, it might be power law model compared to an absorbed power law, right? And so you have some simpler model, so model 1, right? And your null hypothesis is that the data you see was generated by this simpler model, right? And you want to know to what extent can you actually rule out that null hypothesis? To what extent can you say that actually model 2 is better? Okay. So what you do is you would simulate a whole bunch of data from that simpler model, and then you would fit that with model 2, right? Because you would have then a distribution of anything, right? So it could be base factors, so delta log z on the x-axis. It could be AIC, it could be C-stat, it could be any measure of the likelihood. But you would get a distribution down to some value before it turns off, to which point it's indistinguishable, right? So you can't select model 2 over model 1, right? If you're on this axis, if you're at a value of 1, okay? And then you might have a distribution of your real fits, right? So here, shown by the green data. And so if you plot it like this, and you find for the simulated data under the null hypothesis, which was in red here, you find, say, some level, right? If you wanted it super accurate, you could do the 99.9% level. And you basically select all the fits in the green distribution here that are above that, and they're more likely to have no false positive rates or very low false positive rates. Now, this has been used in a number of works. I found them when I was trying to understand this, and today I still find myself getting a bit confused sometimes, but I do find these papers very, very useful. So Johannes' paper in 2014, where this is showing in the blue line the false positive rate, I believe, for 2 particular models that are being considered, so the WABS model and the torus model, for a specific normalization, where you choose the normalization to effectively control how many counts your your on average fitting. So the average here was on the x-axis, sorry, for the bottom panel was around 2,000 counts, actually for both. And then in the right panel, we've got a plot from Baroncelli et al. In 2020, where they use simulations to effectively show that the base factors don't tell you an awful much or an awful lot when the signal to noise of the data isn't above, for that particular Chandra data, above a value of 7. So yeah, I would recommend checking out these papers if you wanted to find out more. Okay, so that's the first two. Then the last theme was model verification. Okay, so this is a very hectic plot, so I'm sorry about that, right? But this, the left panel is what I showed you earlier, where I basically said that each posterior for every source was just the most preferred model with the model selection, right? But it's actually a bit more complicated than that, because if I'm using all of these geometries, I have a lot of models, right? And it just so happens that the data isn't amazing for all of them, right? Well, not many at all, really. But basically, it means that multiple models are consistent within some threshold of being the better model from your model comparison techniques, right? And so it means that instead of having one nice posterior for every source, you actually have something like this, where I've overplotted. So with the thick line on each plot, I'm showing the highest according to the model comparison. And then all of the dotted lines in the background, or the slightly fainter lines in the background, I'm showing all of the model fits that are consistent within some threshold, with also being a pretty good fit, with being maybe indistinguishable. Okay. This is just showing the same thing again. So every single star on each of these panels is just a fit with a specific X-ray model. On the x-axis, I'm just so happen to be using AIC, could be anything. And then on the y-axis, I'm using the base factors. And then these shaded regions are showing the threshold that I'm using, right, just for these particular ones. So some threshold from the highest value down and selecting all of the models that are consistent with that value within that threshold. Okay. So in this particular one, models, whatever they might be, P1, P2, and P6 are ruled out because by the model comparison, but all of these other models are ruled in effectively because of the model comparison. Okay. So the underlying question that we want is that we've got all these models, but is the highest model still a good fit? Okay. So there's visual verification. So I think a number of you have already generated QQ plots in the exercises. I quite like QQ plots because it's essentially kind of like doing a residual plot, but you don't have to bin your data. And so it's much nicer to be able to see very fine features that you might have missed if you're using it some binned quantity, like a residual, or an expect if you use depth, for instance. So in this particular plot, if the line is above the one-to-one line, it means that the model is in excess of what the data is showing, and then it's in contrast, if it's below, it means that there's a data excess. So for instance, you can use it to say that at around 4 kV, there seems to be, if there was a dip, say at 6 kV, it might mean that there was an ion line that needed to be fixed. And I probably should have actually said that on the y-axis is where we're having cumulative data counts. So actually you go along each channel in your spectrum and you sum up the counts as you go along. And so each position on the x-axis does actually also correspond to an energy, which is shown with the insets in this plot. Okay. And then the y-axis is the same, but it's just that you're integrating the model counts instead of the observed counts. Okay. So here's an example of a plot that I made where I've done a fit with 3 data sets in XPEC. Okay, actually, this was in Sherpa. The fact that there are 3 columns, it's just for visual purposes. This fit was just like doing a fit with 3 data sets in XPEC, but I'm just showing each data set in its own separate column. Okay. Now on the left one, I'm showing the first new star camera data. And then on the y-axis, oh no, on the, sorry, bottom panels, I'm showing the same QQ plot, but I've just essentially subtracted the y-axis from the x-axis. So instead of a perfect fit being 1-to-1, a perfect fit would be a horizontal line. And so you see for this particular torus model, it's doing a pretty good job, right? Because a very large amount is consistent with this horizontal line. So in terms of something a bit more quantitative, other than visual checks, you can do what are called posterior predictive checks. So the way I plotted this is not the conventional way of doing it, but essentially the idea is that you have some posterior, you sample a posterior row, and you assume that that posterior is correct, and you simulate data from it, and then you compare the simulated data to actually the real data. Okay. The idea being that if those are indistinguishable, then it should be a good fit. Now, what I've shown is I've just basically summed up all of the W statistics and then divided by the degrees of freedom on the x-axis, and then just split it by the data set. And then this panel is for the total, so just literally adding them together. And it's showing that the simulated distribution does encompass the observed data from the posterior fits. Okay. I think the more conventional way of doing this is to essentially sum up, simulate new data, and then just sum up the range in every single bin of the spectrum so that you can plot the best fit model and then the actual simulated data to see if the data is consistent with the model. Okay. So that was everything I had. So yes, the hierarchical modeling that should be covered in, I think, exercises 2.1 and 2.4. 2.4 is more of an extension, so don't be worried if that one in particular takes a bit longer with the computation. And then, yeah, the model comparison is for